All right, I just started the recording. We are at block 2, and we're going to talk about stochastic OPF with approximate solutions. I'm going to again to the slide I showed before about the scheduling under uncertainty, because in order to end up having a formulation for the OPF, we have to agree where we are actually sitting at, because we're talking about stochasticity, what the stochasticity means, and all these details. So let's assume we are sitting somewhere here, that we have a point that we need to schedule something ahead. We have a deployment point. It might be a day ahead problem, for example, just to make our life easier. We are going to forecast what is going on the day ahead, what is the penetration of renewables, and then we are going to decide what is the optimal dispatch of the generators in order to be able to compensate the uncertainty that comes into the system due to the forecast errors. So I'm going to discuss a little bit each of these parts in this presentation. And we're going to start with the network response, the yellow one, and the steady state points. So if we are going to talk about what can happen in the next day, looking with the forecast ahead, another question that we are going to ask ourselves is that the solution that we need to take from the OPF needs to be secure for what kind of steady state point after the disturbance that is happening due to the generation load mismatch because of the forecast errors. So we are saying we look ahead, we see that we do have a forecast that could be like that. Suddenly we assume that there might be different scenarios that can happen, okay? Let me change the color, okay. So this is a forecast, for example, all right. There might be different scenarios that will appear in real time. And this is a matter of the forecasting part that we're going to see who is going to be there, what kind of scenario. But if we fix, let's say, the one point of the forecast here, and we fix also one of the scenarios, let's say this scenario over here. The question is how the system will compensate this kind of error. Because the system would have generators operating at this point, but suddenly need to operate given this point over here of the area of the renewable energy source production generation. So one way to go, the first thing to think about would be that, okay, in terms of steady state points, one good point to look at and make sure that the system is secure is the one that comes after the response of the AGC, the response of the second frequency control. This is a reasonable assumption of the steady state because it happens and stays there for a couple of minutes, and it's and then whatever happened later on about the redispatch of the tertiary control is something that could be controlled even manually. But we need to be sure that the fast generators that are going to be there to compensate this uncertainty that appears here are going to lead to the system operation in a secure point. So if you see this circle that I have over here, the pre-disturbance operating point, it's easy to say that we can put it inside this circle. So this is a classical, for example, OPF. The OPF is having the constraints of the network, and you optimize for example, the generation output, minimize the generation output. It's very easy to say that for this specific deterministic point that you look at the OPF, you are going to be secure because nothing else can happen. But if you have, for example, this kind of different scenarios over here, then there is a problem because dynamically you might end up to different points outside the safe zone. And this is going to be coming after the automatic control loops that govern the system. And this is why, if you take this into account in your OPF, when you build the stochastic OPF, you understand that you are going to let the system to be secure for the steady state point that comes after the AGC control. You can do similar things for the primary, for example, even though this is a little bit more fast and it's, I guess, a little bit less controllable because it has to do also with the dynamics of the machines, the way that they define all these droop characteristics. But the AGC is something that in the time scale that it comes, you can really influence as well how this kind of uncertainty that appears here, this deviation from this point to this point, will be allocated to the different generators. So in this way, we are going to show later on how actually you can optimize for the reserves as well. Because this kind of difference is really something that the generation should be paid because they're going to allocate the reserve deployment there. All right. So we want to build a decision making algorithms for the stochastic OPF so as to bring these guys inside the safe zone. So if the AGC operates for any kind of point, we end up moving around and staying inside this kind of safe region. The reason that momentarily are making these guys go outside is just because if I'm talking about a steady state point, unfortunately, I cannot say about what can happen in between. I'm only going to ensure that the steady state points are going to be inside. But for certain limits, if you have a very short violation in time, could be dealt. But we start step by step, adding inside the formulation something towards making the system more robust. Okay, so if I focus now to the primary frequency control, one can really write down how the generation that is based on the forecast will be adjusted in order to end up to a generation that is after the disturbance. And the adjustment is happening really based on the droop characteristic of the generators of the system. Each generator has its own droop characteristic that is, as I wrote before, this linear relation between the frequency and the change of the generating power. If you do the calculations, you will end up having this kind of relation for that takes into account the responses of all the generators if something happens and comes to a steady state point given a specific generation load mismatch due to forecast errors, due to outages, due to whatever kind of disturbance you may have and create this generation load mismatch. So you can write this down, and in this way, since you have an equation that actually also is linear, if you want to ensure that the system will be secure given a steady state point that is related with this generation profile, then you can add that in your OPF. Similarly for the AGC. The AGC it's something as centralized. It takes centralized measurements and sends signals to specific generators that they do participate. It is through API controller, as I mentioned before. It measures the frequency from certain points of the grid, and then it allocates the adjustment that needs to be done based on this estimation to the certain generators based on some kind of weights. I call them here distribution vector, the whole vector that consists of all the weights of the generators. So you can write the steady state point of the AGC in this way then, that describes the difference that you can have from the forecast PG, the generation based on the forecast, adapted by this part and having the new generation here. So for example, at this point, I mean, you can see that as it could be as, for example, vectorized, or it could be for each generator, depending on what is convenient for you. But the important thing is that all these guys over here will sum to 1 because they need to compensate this alpha, that is the generation load mismatch. All right. Okay. So again here, if you want to ensure through your stochastic OPF that the system will be secure at the steady state point that is defined by the AGC, it's good to take such a steady state equation, that is linear as well with respect to the generation load mismatch, and incorporate it into your OPF problem. All right. In general, given all these steady state points, you may end up with something nice and linear for the primary, for the secondary frequency control. This is, okay, I just have, instead of alpha, this, assuming that it's for wind power, but it can be anything, any kind of forecast error or generation outage. And you have this linear relationship, but when we go to the redispatch, because it's something that typically is done in real time, given the circumstances of the network at that time, it's not that you could create such a nice linear relationship. So if you go to try to do include such a thing in the optimization, this will result in the problem of trying to find functions that would be the best, and optimization over function is not a tractable thing. So you need to do assumptions here in order to end up having some results with a priori with respect to the tertiary and the redispatch actions. I'll jump up to the forecaster models before moving on to the power flows and optimal power flows. I promised I will show you a little bit of what is the MCMC model. So I'm not having the details here, but it's quite easy to understand through the pictures what it is. So I'll just make some notes here that, for example, we might have a trajectory over here, historical data. And you see that this is, for example, for a specific wind plant, is the wind generation, and it is the trajectory over time. And then you do have many such trajectories, but you do have also the forecast of these trajectories because of the utility or whoever is doing the forecast for that. it's easy to deal with when we are doing the stochastic OPF is to have the distribution of the errors. Because let's say that either we do the forecast or somebody else gives us the forecast, it's good to be able to have such a distribution of the forecast errors, because we need them inside the optimization for sure. So here, because I didn't have such distribution for the errors, I use an MCMC model that what it says is that based on historical data of actual and forecast, I was creating the error signal, the forecast error of all these potential daily data points that I had. And then what you can do is that you can fit within a matrix what is the probability of going from one point here, or maybe I would say, let's assume that this is the error, the forecast error. What's the probability of the forecast error to be from here to go here at the next time point from this? So you check the value over here. You define, for example, the bins of the PV out of the PV or the wind plant output, and you say for all these bins, all these values that you might observe at this specific moment, what is the probability to go to a specific value the next moment? So these two axes here, as you see here and here in this specific plot, are really created based on values of forecast errors that are related, for example, to wind power plants. It's specifically on some data I have got from aggregated wind plant for forecast and actuals from Germany. So the thing is that as you have this error signal, you can create this kind of transition probability matrix that inside here you put probabilities based on the historical. It's very easy to build this kind of numbers in here based on this of the historical data. And this is the result of the data I had that shows, for example, from this specific point, what is the probability to be at a value that will be quite close to this, that, and will be 6. And the probability is getting higher as you are closer. As you see, that's why you see this diagonal. Just don't get confused. This is 40 over here, 40 over here. That's why the diagonal is like that and not like that maybe some people are used to in this kind of probability transition probability matrices. So the reason you may do such a thing is that because you do have historic data, forecasts and errors, but you might not be able to have enough data to describe your errors in the next day. And by this, you can create this kind of forecast error generator. And by generating these potential errors. So the way I did it here, I normalized with the forecast, and that's how, when I had a forecast of a specific variable, I was able to say, okay, given this specific forecast, the potential error scenarios are going to be here. And I applied it to this specific forecast green line for 24 hours and see how, for example, I don't remember, maybe 10,000 scenarios are coming out of the generator. The final actual value for this specific case was this, but this was trying to get some kind of of range of where the error could lie in. Okay, time is flying, and we are going to go now a bit more on the optimization side to go and describe a little bit how we are going to really define the stochastic OPF, and with respect to the constraints and all this kind of steady state points and stuff that I described to you. The first thing to say is that the typical OPF is, you can assume that it is based on the forecast, and you can write down, you saw all these equations that were written on the first 2 days regarding the OPF. You can say that one of the variables that was there constant now is something that corresponds to a forecast, because we are going to see now how we are going to translate that to a stochastic problem. So there are decision variables X in the OPF, classical decision variables. We do have the forecast variable that is separate. We have made it separate. We have the objective function, the minimization of the generation costs, and it's a classical OPF problem. Okay, now the thing is that this forecast cannot be perfectly correct. There are errors, as we've seen also in the different distributions before and the examples, and we need to create a problem that gives a solution that is robust with respect to these errors. This is a reformulation of the problem in a robust way. So what does it mean is that you're going to minimize your objective function, the minimization of your generation, subject to X, your decision variables, and your constraints you have in the system. But this time your constraints are actually going to be a lot more, because you want to satisfy them for all delta that belongs to a specific set. So let's assume this kind of rectangular set, for example. So for all delta that are inside here, that are infinite many actually, you want to satisfy this kind of constraints. In general, for a general problem, this is not it's not easy to be solved. But if you have, for example, linear cases, then you're able to solve a problem very easily in a robust way. What the problem comes when you have, for example, let's say you have linearized your system and you are happy with that, given the specific parameters that is creating not that bad linearization. The question here with the robust problem is this set well defined? So how one would say whether this box is big enough or small enough in order to ensure that the system will be operating in a secure way, given the solution, let's say X star, that comes out of this problem. You might select such a box, because this box comes from the knowledge you have for the uncertainty. You might select such a box that would be huge, and this will result in a very expensive operation, because you add and more constraints into the system, into the optimization problem. Or you might select to have a very small uncertainty set somewhere that you would like to be robust, but the reality is that your uncertainty lies outside this kind of box, and then you will end up to an unreliable operation. So this kind of solution, if this delta n is very small, then it doesn't make a lot of sense, because delta might live outside them. So how to define that can be tricky. We will go through one way of doing that in a kind of efficient way later on. And the second thing that I already mentioned is the fact that this kind of problem, when we go further and have complicated constraints, nonlinear, non-convex, it's not something that could be really solved. And that's why what we like to do at this point to make our life easier in the way we are getting a solution that makes sense is to relax a little bit the constraints. Relax them in a probabilistic sense. So before we wanted the constraints to be satisfied for all delta within this big capital delta set. But now we are going to allow some of them, a very small amount of scenarios, to violate our system constraints. And this is actually described through the so-called chance constraint over here. So you do have your constraints that initially want to be satisfied in a robust way, but now we are relaxing it by saying that these constraints are going to be satisfied with a probability at least bigger than 1 minus epsilon. And this is something, okay, they write it in this way in many manuscripts. Epsilon is a design parameter and determines the desired violation level of the probability. So you can imagine that if epsilon is very small, you end up going to your robust problem, right? So if epsilon is very small, you want this to be satisfied with probability 1. So you end up with this one. And okay, I didn't mention here that of course delta lives somewhere. So this kind of space that delta lives will be creating the fact that as epsilon goes closer to 0 and you have a more robust requirement for your system, for the solution of this problem, then you may expect that the cost of having this solution is gonna get higher. So this is a way of creating a trade-off by controlling this epsilon of the cost that you are going to have in the operation of the system, given this X star that is going to come out of this algorithm, and the security of satisfying this kind of constraints with certain probability. That is defined by this epsilon. All right. Solving chance constraints can be very difficult in general, and that's why one way to go through them in a more easy way, I would say, is through randomized optimization, because it's a database technique. It uses samples to learn how to get the desired performance that you need. The other good thing that it has is that you can generalize the results you have from seen samples to unseen realizations. And you could provide confidences about that your predictions are correct. There are certain methods that I have been working on randomized optimization, that they have their pros and the cons. And I'll go through a couple of them and show you how you can use them in the OPF setup. Okay, the first one is the so-called scenario approach. The scenario approach, the good thing is that there is no assumption about the underlying distribution of the uncertainty. So we don't need to assume anything. We're either going to use data or maybe constructed data as we go, based on, for example, based on this MCMC generator. And it can guarantee a priori, it can provide guarantees a priori that the chance constraint is going to be satisfied with a certain confidence. The downside here is that it requires convexity of your problem with respect to the decision variables, so it cannot be applied to the typical AC OPF problem, because we do have this non-convex constraints over there. Okay, there is another method. I'm going to go a little bit more in detail to each of them, but just summarize, I'm summarizing them. There's another method that it has a good thing that it creates a mixture of randomized and robust optimization. And in this way, there is this kind of problem here, is that we require convexity is not a problem anymore. So there is no particular structure required with respect to the decision variables. And all the other good things are kept as well. Theoretically, this is something strong. Practically, given the fact that, as I will show you later, you are relying on a robust problem in the end, is not giving us a very good outcomes for non-convex problems, because you cannot really solve easily the robust problem in the end. Yep. So here I'm just summarizing the fact that these two approaches could be used on different OPF formulations. The DC OPF is something that is a linearized problem. So both the scenario approach and the probabilistically robust design can be used. The convex relaxations that you've seen so far is something that also could leverage these two methods. But if you want to go further to unit commitment problems, that mixed integer take place, then you can take advantage of the second method that really does not rely on the convexity. The heuristic method that I talked before about solving an OPF in an iterative way is something that neither of these two methods could be used, but there is another one later on that I'm going to talk about that we could use on this AC QP as well. So briefly talking, because time is going so fast, the scenario approach is it's something that says that when we have our chance constraint problem, you can see it like that. It's quite similar with what I showed you before. We have the delta live that lives and certainly lives inside a specific space. We have an inequality constraint, and we want it to be the whole probability of satisfying this constraint would like to be at least 1 minus epsilon. The scenario approach suggests that we can substitute this chance constraint with a finite number of deterministic constraints that are using a different samples of the uncertainty that we have, the uncertain variable that we have. And what they are proving is that there is a specific bound for the number of the scenarios you are going to use that is given by this formula over here. So your bound should be bigger, so your number of scenarios to be used here in a deterministic way should be at least 1 over epsilon, blah, blah, blah. Depends on Nix, that is the number of decision elements. Yep. On beta, that is it's called confidence, but I'll show you in a bit what it means. And the violation level, of course, that you see over here, right? So if you would like to create a more robust problem by saying, I want an epsilon to be very small, you see directly that this affects the lower bound of the scenarios that you need to take into account, because it creates this, the 1 over epsilon, it increases a lot the number of scenarios that you need to take into account. And that makes sense as well. And also shows in this transformation as well how, again, the cost will be increased because you add more and more constraints into your system. All right. Just to put a comment on what is the beta, the beta is the probability of this whole thing to hold. To hold, it's not one, it's to hold with 1 minus beta probability. They call it confidence, the beta itself. I don't know exactly why, maybe 1 minus beta sounds for me more like the confidence that you have, because it really shows a big number. But anyway, they have called it like that, and it means it gives them a little bit in the proofs they do this kind of freedom to allow for such cases that the whole thing will break, but it's really very small number here that you would like to use ideally, and this is not influencing the number of scenarios a lot. So it doesn't play a huge role here, practically. The second method that I'm discussing here is the probabilistically robust design, and it's something that has 2 steps. What they try to do here is to convert the initial problem, chance constraint problem, to a robust problem, and they want to answer the question, what is the box, what is the robust set that we would like to be confined in, so to be robust for. So in the step 1 is uses the scenario approach to find bounds for the uncertainty elements. And for example, we do have this 2-dimensional space over here with so many scenarios. The scenarios over here will be used in order to find bounds. So for example, you might determine an optimization problem with boxes, and you will try to find what is the box that contains the n number of scenarios that you have extracted based on the decision variables that depend on the specific optimization problem of step 1. If you have a box, then the decision variables to define the box, such a box would be twice the number of uncertainty. And that's why this is the number of scenarios we need to extract. Finally, by getting this number of scenarios, you can define easily what is this set. And by having this set, they have shown a proof of changing the chance, transforming the chance constraint to a robust problem. The tricky thing here, compared to the initial robust problem I mentioned, is that we do know that this chance constraint will hold for the solution that you are going to get out of the robust problem, right? So it's not just a randomly picked set over here of uncertainty, but is defined based on the step 1 that in the end leads the probabilistic guarantees to hold for the solution out of this robust problem. Okay, so going back to the OPF problem, we like to solve it with this chance constraint way, either with, you can use the one or the other depending on the type of the constraints you have here, inside over here. One point I will show in this kind of block is given the approximations that we do, like linearized power flows. I'm going to talk about, for example, the DC power flow, just to keep things simple. And it can be formulated like that. So you can see here the deterministic problem. In the DC OPF, we don't have voltages anymore. We do have the decision variable that would be just the generation dispatch. So this is a very simple, if you see the deterministic problem, it should be a very simple DC OPF problem, that you have the generation cost to minimize. You do have the equality constraints over here, and your inequality constraints. Here you see I kept again this delta F a bit separate, because you will see the connection with the chance constraint problem. So the delta here is the uncertainty that we have, and we have translated these constraints to this chance constraint formulation. One thing that is a little bit tricky here is one of those two constraints in this specific case. Can somebody imagine which of the two is really tricky? What we want to say here is that we find an X star out of this problem that is going to satisfy these two constraints for the delta living in somewhere in space, so many scenarios of delta, with probability bigger than 1 minus epsilon. Do you see a problem here in this question I pose? So you can imagine that if you have, for example, something like that, in a chance constraint, so an equality constraint within the chance constraint, and you want to satisfy this constraint for every delta in this space, and you need to find only one X out of that, you understand very quickly that this is not feasible, right? Because if you have an equality and you change delta based on the different scenarios that may appear, and X star, it's something very specific, it's not changing, then this is not going to be feasible. So this is something that it really motivates the fact that we can use this kind of steady state point response of the system in our benefit to make this equality constraint disappear. Because the equality constraint in this case, it really shows the power balance. But the power balance is something that can be automatically satisfied given the fact that we are allocating the errors that they appear in the generation load misbalance they appear, we do allocate it to the generators according to our distribution vector. So in control theory, these are called affine policies, and this is something we introduced in this kind of problems in order to be able to create this closed loop of seeing what is actually the generation output and all this and be able to determine all the constraints exactly, given any kind of error that appears in the system due to your uncertainty variables. So this is something very important to help us open the actually the door of so many optimizations, stochastic optimization techniques to be applied in such problem. Because without using that, then we wouldn't be able to say a lot of things. So finally, this kind of equation might be motivated by the fact that we care about what will happen in the system in the steady state point, but mathematically also helps us solve the problem in a tractable way. Okay, just some comments about the scalability of these two methods. After we have created this kind of function of x with respect to delta, we end up having just inequalities in here. Okay, this is just again a lumped way of showing this. They don't, after doing this change of the variable with the affine policy, this x does not correspond exactly. This equation does not correspond exactly to the previous one, but it needs just manipulations, simple manipulations. But in the end, you end up again with this type of inequality here. And the question is, what happens when we really have a lot of decision variables, or what happens when we have a lot of uncertainty variables, because we have a lot of renewables, a lot of different kind of signals. So in this specific way of solving this TCOPF, the fact that the n number of scenarios depend on the decision variables in the one case and on the number of the uncertainty variables on the other case, it's something that is not really in the end going to create any problem in the scalability because of this linearity of the constraints. As you see how many we have, even if we have a lot of scenarios n, then putting this constraint and one under the other, we can just do pre-calculation in order to find the epigraph of these constraints, and then we solve the optimization problem with one only constraint as in the beginning. And the same holds for the robust case as well, because you can also do the pre-calculation to find out what is the worst case function that is here, function, I mean number that appears there, given all these different scenarios that are to be included for this robust case. And again, the system ends up having a set of constraints as in the beginning. So that is the, I guess, the good part with this kind of simplifications. They scale very well, and we get some solutions that provide some kind of guarantees with respect to security, given the assumptions we have done, of course. Showing here a few details on how the more specific problem is formulated with respect to the DCOPF. I have added here the n-1 security constraints. It's just to show that you do have the minimization of the quadratic cost function of the generation. Then you do have the power balance for that is based on the forecast value here. You do have your chance constraint that you have the line capacity limits inside. You do have your generation capacity limits inside. Pay attention that the generation capacity limit is now something that is to be respected for the new steady state points as well. So you remember that this is the dispatch that is depending on the forecast, because as you see, it's going to be determined by the balance given the forecast value, but the inequalities that are coming here shows that we can actually satisfy the generation limits for the scenarios that we are going to take into account. And when I say scenarios, the scenarios here, they will appear in this P mismatch. This is the generation mismatch. This is where the scenarios are going to get into the system in this formulation. The line capacity limits here, you can, because we're talking about the DC OPF, you can represent them directly like them with as a function of the injected power. So you can end up writing actually like I don't know, I would say alpha multiplied by the generator. And wait a minute, blah. Yep. And then you have also the other things inside here. So you can you see that's just a linear way, nothing more complicated, because this is coming from this equation over here. That is actually the injection that appears in every bus. So it was just to give some more details on how the DCOPF can be formulated. As mentioned before, we are going to ensure that the new steady state points based on the new realizations will be secure. So if we focus on this point of time, that we have this forecast of the wind, and we do take into account in the optimization all these green scenarios, then inside the optimization, we are going to be securing all these scenarios to result to not violating any of the constraints that I just mentioned. Here are a few plots for a toy example of a 30 bus network. It is based on the formulation I showed before. And let's focus on this part here, that on the y-axis, you can see the probability of violation of the constraints, but you can see the empirical probability. So, for example, what I have done here is that you're solving the problem of the chance constraint DCOPF. You get a solution that you think, okay, that is fine, and then you can evaluate the solution given, for example, 10,000 scenarios that you haven't been using within the optimization. And then you can see what is the probability of observing violations in the system. Here, in this case, I have this 24 hours. And in this case, in the case below, it's a chance constraint problem, as shown just before. And in the above graph, you see the deterministic solutions. The solution, the empirical probability based on a solution that you use only the forecast value, not scenarios. So there are different case studies based on different load profiles, just a couple of different load profiles that were assumed to be just constant like that, fixed like that. And we have some wind power generators, scenarios generated by this MCMC algorithm that I showed you before. As you observe, the probability on many different cases of the loadings, the probability of having insecure case could go very high. This is like almost 80%. And of the scenarios are 80% of the scenarios of the 10,000 scenarios we're really violating constraints of the system. Whereas if you notice what is going on with the chance constraint case, it is scaled actually, and here you see this point over here is 0.06. So it's a very, very small. The epsilon used in this case study in order to find out how many scenarios we need to extract and use in the optimization was assumed to be 10%. And this is what I was thinking that I will satisfy. And indeed, it satisfies this 10% because this is way, way, way below, smaller than the 10%. But the thing is that if you remember, as if you have a desired violation, let's say not desire, but maybe acceptable violation level, that means maybe you are fine with that because you're going to pay a bit less. You have this kind of trade-off in your mind. But if in the end you end up having a lot smaller empirical violation, it might be that, okay, you achieve your goal with respect of security, but with respect of the cost, you might be a little bit conservative. But this is something that it comes with this methodology here, that it gets some results that are a little bit more conservative than what you would like to see. Okay, and here, I guess this would be my last slide for this block. I would like to show in this graph for this specific example how the cost was increased from when you were moving from the deterministic setup that you didn't consider any kind of scenario. You didn't think that there is a forecast error. You just trusted your forecast. You solve the problem, the OPF, DC OPF problem, and you end up to this point. But then when you realize, okay, there are scenarios that may appear in the next day that you should consider in your optimization to be robust, then of course, because your feasibility space gets more restricted, you end up increasing your costs, your operation cost. And this is showing how you go from different levels of epsilon closer to 19, up to 99%, and how the cost is increasing that way. Of course, you may think, okay, you might not want to do this kind of extra cost in your system, but you should be comparing that all these points over here are accompanied with this probability, with this kind of probabilities of being secure, while this one, it can be something totally unknown, unpredictable. In the specific case study I had, it was for this case study I ran was up to 30% example. You saw in the previous graph that it could reach a lot worse cases, like even 80% of empirical violation probability. So we have this epsilon. We can use it to trade off security and cost. The more secure we want to be the solution, then we have to pay for that. And this is where I would like to stop now. If you have any question, please write in the Q&A or please raise your hand. We can do a break and we will be back in just maybe we don't have a small break, sorry about that. We're going to have a big break and we're going to be back at 11 o'clock. All right, see you in a bit.